Hello again. Tonight's topic is observing nothing. You can kind of describe it as a YouTube clickbait kind of title. Those things actually do work. But we'll talk about finding places in the sky where there isn't much of anything, so we can observe nothing, and what that means and why it's different for different types of telescopes. So for those people that are used to making astrophotos, in order to improve the quality of your pictures, you do something known as taking darks. What this typically means is you're going to cover up either your telescope aperture or opening, or you're going to put a cap on your camera, and you're going to take some pictures of the same duration, the same exposure level as you would for whatever target you're going to shoot, and take a picture of nothing. But the reason why you're doing this is if the electronics in your camera produces heat and it's like over on one side of the image, or you have stuck pixels like red, green, or blue, or whatever pixels that just aren't going to show you what's really there, they're going to show you like just red, always red, then by gathering a dark, you will have a background that you can mathematically remove during post-processing to make the signal to noise ratio, the quality of your image, the contrast of your image, that much better. And in radio astronomy, you do exactly the same thing, but what you're doing there is you're taking out what is known as the heat of your system. The heat refers to the Kelvin value of the metal in your antenna's arms and body, and in ambient air, that metal will have a certain temperature. You are bringing in a baseline of that temperature into your radio receiver before you ever start receiving signal. So it's kind of like taking a dark, but in that case, what you're doing is you're saying, well, I know what the signal is going to be. So what I'm going to do is I'm going to disconnect the antenna, and I'll take an image with it connected, and now I know what the difference is. So you're actually inverting that. You're saying, the antenna produces a certain level of heat. There's a certain Kelvin temperature value associated with the metal of my cabling and my antenna. And if I disconnect that and make another measurement, I'm making a measurement without that. So now I can invert that and subtract that off, and I can improve my radio signal capture. Same thing. It's all about improving the signal to noise ratio. And typically you do it by closing it off, doing a dark. But this kind of dark is too near perfect a dark. If you want to get rid of the active noise sources, the static stuff or the random background noise, covering things actually induces that. So if I say I've got a nice big Newtonian, and I cover the front of the Newtonian, and then I take my dark, the fact that you covered the tube, if you don't have the tube current circulation fan going, you're actually capturing as part of your dark the heat inside the tube as part of your dark. So you'll be not subtracting an accurate dark. The same thing is true in radio. If you disconnect your transmission cable, that's going to be there when you capture your signal. You need to maybe disconnect the antenna from the cable and just measure the cable, so you can accurately subtract out the bits that you don't want from the true signal that you do want. The better way to do this is leave your rig intact, but capture something that is nothing. And we'll discuss what nothing is. There's two different ways of describing the nothing. One is by the electromagnetic spectrum of your instrument. So if you happen to have an optical telescope, you want a nothing in the sky that has near nil infrared, visible, or narrow band, such as hydrogen alpha. In radio astronomy, you want whatever you're tuning, whatever frequency band you're tuning on, you want something in the sky that doesn't produce any significant signal in that range. Depending upon what type of instrument, what type of sensor you're using, you would want to select something else in the sky to be your nothing. But if you're shooting the sky, unlike, taking your camera and putting a a metal black cover over the front of it, the nothing of the sky will always be more than nothing. It will be a little bit of something. It might be darker, but it'll be always a little bit of something. There are things that you do want to capture and subtract out of your image that you can't subtract out if you're covering or disconnecting. And that is something known as off-axis or side lobes. If you have a telescope and you point it at the sky and there happens to be like a bright city over in one corner of the sky, if you cover the telescope and then you take your dark, you will not be subtracting out the light from the city. You'll still have that in your final image. But if you pick a spot of the sky where there is not much of anything and you shoot that image, you'll be getting the light from the city and you'll be getting the heat light from your electronics, and you'll subtract out a more realistic value for dark. Same thing in radio. In radio, if you have an element-based antenna like a Yagi, you see the cross ribs. It's not inside of like a cylinder or a big cone. It's just open elements. Well, there's outside temperature that can heat up the open elements, and therefore, if you just disconnect the antenna, you don't know what your side lobes are. So you want to get rid of the side lobes. Well, the only way you're going to do that is pick a part of the sky that has very little signal in it on the frequency range that you're tuning and point it there. That way, if the structure of your antenna has spurious side lobes on it, you'll be subtracting them off. You don't want a true absolute nothing like you're trying to shoot for by disconnecting or covering. You want a more realistic nothing. So if you're looking for an optical nothing, how big a nothing does it have to be? Well, if you're an astrophotographer, you'll usually be shooting about 3 degrees of sky. So if you look up in the sky, the moon is a half a degree. So 6 times the diameter of the moon. If you're shooting planetary images or small things like globular clusters, that's way too big. If you're shooting the smaller things, half a degree. So if you could find a relatively dark spot of sky that was about a half a degree, that would be a sufficient nothing for you. Now there is, you probably see this on YouTube videos, Boötes Void, the great nothing as it's referred to. Yes, this is an area where there are so few galaxies that it's considered to be nothing. If you look at the average density of galaxies across the universe, you'll find that there are so few in this void that it's a great void. It's a great nothing. Look inside that green circle that's there and you go, I see all kinds of stuff there. Oh, well, think about it this way. This is the stuff that is either in front of the void, closer to you, or behind the void, farther away. What you're not seeing is the stuff that's in the void itself. The void is not truly perfectly spherical or circular. It's got feathered edges and such, but it has 3-dimensional density. So if we go looking at all the galaxies in that part of space and we measure their redshift, we find that there are things in the foreground at a certain redshift, so we know their light years distance, and there are things in the background that we know their light years difference, and maybe a small smattering of even closer in our galaxy stars that just happen to be in that field of view. So if we subtract out the galaxies in the back and the galaxies in the front and the stars that are in our galaxy, what we're left with is a huge space of nothing. So that's the Boötes Void. So as I was saying, nearer stuff gets in the way. So if you're looking at what has been designated to be a void or a nothing, then, gee, if there are galaxies in the foreground or stars in the foreground in our galaxy, the entire diameter of the nothing will be not what you can use. It'll be a piece of it. So you want the part of the nothing where you don't see the other galaxies and you don't see the local stars. So you want to ignore the stuff that's nearer to you. And the same thing's true about the farther away stuff. The stuff that's farther away, those galaxies that have been redshift identified as being in the background beyond the void, you want some part of the sky where you're working, okay, I see no galaxies in the foreground, I see no galaxies in the background, and I see no stars in the foreground. And if you can get about a half a degree out of that, that's your nothing. Now for radio astronomers, there's a radio equivalent of nothing. The cosmic microwave background, or the CMB, is kind of everywhere. That's this picture in the upper right. That's the cosmic microwave background map. You'll see that the darker areas are where there's less signal. Right there in the center, just below the equatorial area, horizontal line curving around, there is the Eridanus void, or supervoid. It's in radio, it's in microwave radio, and it's even bigger than the Boötes Void, but it's oddly shaped. And also it's in the southern hemisphere, so unless you're Australia kind of thing, it's probably not going to be something you could use here in South Florida. But the interesting thing about this is, if you're looking for a nothing and your telescope, your radio telescope, observes in the short wavelengths, it's harder to pick that because those are going to be higher energy targets. If you look in the lower frequencies, the longer wavelengths, those are things that are more red shifted. They're more off into the background. Those are easier to discount. And they're also older, newer things in astronomy and astrophysics produce higher frequency, higher amplitudes of radio output. Right? If you're looking at a pulsar, relatively speaking, it's early in its life. If you're looking at a quasar, the same thing. Once they've gone through that spell, they'll reduce their energy output and their wavelengths will descend, and they'll now be closer to infrared. And if you remember in a previous discussion, I talked about things that are descending the redshift, and when they go below infrared, they just disappear. That's the kind of thing you're looking for. But you also have to know, what wavelengths am I looking at? Because you might go, well, look at that thing in the upper left. There's an opaque part of the sky. It's a big black blob. That's nothing. Actually, that's not nothing. That is a molecular dust cloud called Bach globule. And this particular one is called Benedict 68 or B68. If you look at it in visible wavelengths of light, it's a big black blob. It's a lot of dirt, and the dirt obscures the starlight in the background. But if you shift it from visual light to, I don't know, 2.16 micron infrared, you can see through it like it's not even there. So if you're doing optical astronomy and you happen to have B68 in your field of view, that's a great nothing for you. If you're doing infrared astronomy, that's a lousy nothing for you because you can see right through it. Not every nothing has to be a complete nothing. It just has to be nothing enough. And just for comparative speaking, nothing or no thing also exists in mythology, literature, and music. How many people know about The Nothing from the movie The Never Ending Story, the kids' movie? There you go. Who knew it was from a German book?
Yeah.
This is not the nothing we seek. So the nothing has to be a nothing that, it can be the right kind of nothing for your telescope type or your instrument, being a camera or radio. But if you're in the northern hemisphere and you pick a nothing that's in the southern hemisphere, good luck with that because you'll never be able to see it. Pick a nothing in your hemisphere. If that CMB cold spot, which is in the southern hemisphere, wasn't good enough for you, then you need to pick another one. Hey, there's another void, another radio void called the Capricornus void, obviously in the constellation Capricorn. It's kind of a mid-latitude constellation. We get to see it for a while during a portion of the year in South Florida. It's even bigger, but that's a radio cold spot. A more northerly one is the Northern Local Supervoid. Now, I like how astronomers or astrophysicists will pick. It's not just a void, it's a mega void, it's a super void, it's what kind of superlative do they use next time when they find one even bigger and darker? It's the humongous void. Yeah.
Ludicrous void.
It's the there you go, it's the ludicrous void, or the plaid void. The interesting thing about this one is it's 339 million light years in diameter. It's just a big spot of nothing between the constellations Boötes, Virgo, and Serpens Caput. I like that name. The Serpens Caput. This void is so large that all you get is the right ascension hour angle and the declination degrees. It's got feathered edges on it. So, well, what coordinates do I enter into my astronomy program or my telescope? Just pick something in the middle, like 15 hours, 30 minutes, 30 seconds. 15 degrees, 30 minutes, 30 seconds. Just pick something in the middle. And if it's not dark enough for you, you got plenty of wiggle room there. So let's say you do pick the right kind of nothing for where you're living, but it's only out during certain times of the year. Or you pick a particular night to go observing in. You can't see it that night because, like fern forest, clouds, rain, or a tree got in the way, or a building is in the way, or there happens to be a street light in the way. You can just pick another day to come look for your nothing. The beauty of this is when you're shooting these kinds of nothings as you're dark, you need to get the duration correct. So if I want to shoot a globular cluster as my actual image, and I want to give it 3 minutes per frame, then I'm going to shoot a 3-minute nothing. So I keep it balanced. Now, when I want to point at nothing, do I just, wherever the nothing happens to be, if the nothing's low on the horizon, would I want to shoot that as my nothing? No. If the nothing's directly overhead, would I want to shoot that as my nothing? Well, that's better, but still not quite right. You want to shoot your nothing when it's nearly overhead and it's not near to anything that would be noise to you. And yes, places like Jupiter make radio frequency noise. You want the noise sources, be it light or radio, to be kind of at your back over the horizon, or in the case of the sun, you want it to be well set behind you by a number of hours. You don't want to shoot your nothing directly overhead. You want to shoot it a little further along than overhead. So you're getting the thinness of the atmosphere, but you've also got all your noise sources at your back.
Why not straight overhead?
Oh, because straight overhead, you're going to have other interference sources that are in the sky as well. Those will be more easily received if you have any amount of moisture in the sky, because they'll be reflecting. So if you have city lights around you and you shoot directly overhead and you have humidity, you have the maximum amount of reflection from the city lights, other than shooting down the horizon at the city lights. So if you shoot a little off directly overhead, you're going to get less of that reflection. Well, why not pick the best nothing you can find? Because the best nothing, the most absolutely perfect nothing, is not observable. Somebody says, what's the best picture of a black hole? The best picture of a black hole is you can't see the black hole. So the 3 pictures at the bottom are, the one in the lower left is the actual false color image of the black hole at the center of our galaxy. But it's in radio frequency, not in light. So they remapped it to colors to let you know what the radio intensity was of a particular wavelength of energy. The second one, that's computer simulated. That's got nothing to do with what you'd actually see. And then the one on the right is, it's a pretty picture by an artist. If you say, I want the best possible nothing I can get, it's a good thing to shoot for. But what you want is not the best possible nothing. You want the nothing enough. You want a nothing sufficient to your needs, be it optical or radio for a particular wavelength. Nothing enough, but not a perfect nothing. So I remember this back from 1995, like as if it was yesterday. This was the first Hubble optical visual band deep field image.
Yeah.
And it was actually a matrix of 13 frames, 13 images, and they shot this over a 10-day period. The area that they shot was something that from ground-based observatories, they thought was a dark spot of the sky, a nothing. So from the ground, this was nothing. And the size of the nothing was about the size of a tennis ball at 100 meters. So if you could hold up a tennis ball, if you had really long arms and you could hold up a tennis ball at 100 meters, this is the amount of sky that they were looking at that they thought up until this point that they took this image was nothing, just to prove to the unbelieving people that all that dark stuff you see out there is not really dark. It's actually, it's not just full of stars, it's full of galaxies. So there's a couple of stars in here that are in our galaxy, but most everything else that you see illuminated in there, those are galaxies farther than our galaxy. When you go to shoot a nothing, if your equipment is sensitive enough, what you initially pick for nothing might not really be nothing. I'm going to do astrophotography and I've got 3-minute frames, and you shoot what you think is a nothing, and all of a sudden you come away with, there's 3 galaxies there. You might want to pick a different nothing. But if you know where the 3 galaxies are, you can always subtract them out. If you're not on par with the Hubble Space Telescope or the James Webb Space Telescope as far as sensitivity and amplification and exposure duration, you can probably pick whatever, HST or JWST uses as their contemporary nothings and shoot at least there, because you're not going to see anything. So there may be people that realize all these nothings, all these voids, they sound pretty big. Sounds like there's a bunch of them. I thought the universe was supposed to be uniformly flat. Now, flat doesn't mean like flat Earth. Flat just means the density spread of objects throughout the universe was close to being uniform. It was kind of like if you're making a crepe and you spread that crepe out really thin on the griddle, and then you cook it up, there'll be air bubbles in it, little tiny air bubbles. So there'll be voids, but in general, the crepe is smooth. Same sort of thing. The quantity of voids that we know of, ignoring the voids that we don't know, that are smaller, hopefully, even if you subtract those out of the cubic light years space that is the known universe, the voids are noise, they're linked. Here's an analogy for you. Consider all of the asphalt and cement covered road surfaces in the Los Angeles area. Everybody always complains about potholes and how big the potholes are. If you take all of the non-potholed surface and you added all that up in the LA area, and then you subtracted out all the bigger and all known smaller potholes, the road surfaces in LA would still be considered smooth. Because when there's a big pothole, it's not anywhere near anything else, and there's so few of them. If it's a small enough pothole, you just ignore those because it's just a little bump in the road. But for the most part, the road's smooth. Same thing about the universe. For the most part, the matter in the universe, the baryonic matter, the actual material, is fairly spread out. But there's a cosmic web of the denser parts of all the baryonic matter. And between those denser spots, there are these voids. And the voids are kind of like falling off a cliff, void, lower density. So there's very little in there. But you might find a void where there's a thread of galaxies running in like a spider web around this void. And inside the void itself, there would be less than 100 galaxies, whereas there's thousands of galaxies on the spider web around the outside. So if you happen to live on a planet in one of those galaxies, and the next closest galaxy to you was 1 million light years away, and there's no closer stars because you're in a really small galaxy, like a dwarf galaxy, then your night sky would look pretty dark. You would have an excellent time finding void. Here in our neck of the woods, there's a lot of stuff out there, so you have to more selectively pick your void. So in conclusion, sure, you can go ahead and cover your aperture, your imaging chip, disconnect your antennas and your cables, and that's a way of capturing darks, a form of nothing. But if you want a better nothing, then you want to observe with your rig fully intact. And you want to pick a nothing that is as nothing as appropriate for your particular type of equipment. But you have to pick a nothing specific to what you're doing, be it optical or radio, to make sure that you don't get something that is noise. And while a void may be spherical and big, there may be stuff in the foreground and background that makes the stuff in the foreground and background not nothing. Pick your nothing wisely and make sure it's a nothing you can view from where you're at. So if you're in the northern hemisphere, don't pick a nothing in the southern hemisphere, you'll never see it. And the best way to observe your nothing is near but not exactly overhead and point away from sources of interference. It doesn't have to be a perfect nothing. It just has to be sufficiently nothing. And then, of course, lots of links. And it was interesting to find that there is a Wikipedia site for a lot about nothing.
What you do about nothing.
Well, Much Ado About Nothing. That's actually a movie, yeah. So, comments, questions,
You go deep in these things. A lot of work.
This took me 3 weeks to put together, off and on, because I'll put the baseline down, the gist of it. It'll be maybe 8 slides. And then over the course of the coming days, little brain farts will go off, and I didn't talk about this, and I should talk about that, and I should compare this with that, and what about this? And I just keep adding content to it until voila, 24 slides. But then there's the front slide, the opening slide, this slide, the links slide, the all about me slide, and the conclusion slide. So you're going to take 5 or 6 slides off of that, around 20 slides. But up until the next to the last slide, there was not a lot of heavy math. And it wasn't really math. It was just sums and scientific notation.
I thought this was going to be a nothing presentation, but it wasn't.
Yes, it was much ado about nothing. So, Jay, you're used to shooting darks.
Right.
Well, is this an interesting, maybe different approach to shooting darks?
I don't think so.
That's fine. That's fine. You got to stay with tried and true and prove it in your past.
Well, tried and true. And because you can control the temperature of the camera, and you can do that even if you take it out of the telescope and bring it in the house.
Mm-hmm.
What you tend to do is you create a dark library in advance.
Right.
And so you'll have sometimes as short as 10-second darks. And normally when I do darks, I do at least 30 of each. So, I might have 10 seconds, 15, then I go to 30, a minute, 2 minutes, 3 minutes, 5. Usually 10 and 15 is where I end.
Mm-hmm.
And so if you're doing 30, 15-minute images of darks, your camera's running for a couple hours in the house. But once you have the library, you really don't have to retake them. A good 6 months.
Mm-hmm. So, how do you take out local light pollution?
Well, the camera's in the house. The camera's completely covered in dark. So the only thing you're really trying to get is, the
electronic signature of the camera.
Correct.
Yeah, yeah.
And of course, you're getting bad pixels too.
Yes.
There's always bad pixels.
Yep. The stuck hot and the stuck cold are really easy. It's the warm pixels that are random. Those are the hard ones to prove. But there's algorithms for doing that. Okay. I wasn't expecting to change your mind, because this is something I sort of looked at and said, well, how do you do a dark using a large observatory camera that you can't necessarily remove from the telescope? How do you cover to shoot?
That's true. That's true. You can't, you're not going to go to, a Lowell observatory and try to cover the front of the telescope.
Well, algorithmically speaking, there is a software driver method for doing that. If you look at the camera chips themselves, you don't actually get to use all the rows and columns that the imaging chip has. There's at least one row and one column along the edge that are completely covered. They're just as sensitive as the actual pixels, but they have no ability to receive light. And if you were to talk to the driver writer, the driver developed the software driver developer nicely, he could actually send a command to the camera that would allow you to read the dark pixels of the camera chip itself. So you don't actually need to cover the camera or put a cover over the chip, because the chip has its own built-in covers. But I've never seen that except in the astronomical professional grade drivers doing that. The amateurs tend to just cover over the camera aperture, or take it indoors and shoot in the dark, or even put it in a bag and shoot it in the dark. but I've never seen a driver in, popular astrophotography programs where they could talk to the camera and say, "I'd just like your dark pixels, please."
Sure, sure.
But yeah, that's been possible for, I don't know, 10 years or so from me having looked at camera chips.
Well, it's like flat frames. A lot of people will take what they call sky flats.
Yep.
So as the sun's going down, they look for an area of the sky that's still got some light to it.
Yep.
And that relatively the light is kind of the same. But the problem is every now and then you do that and you pick up a star or two that you can't see.
Well, that's why you bring along with you a low thread count, 100% cotton pillowcase.
Yep.
And you put that over the front of your telescope so it creates a diffuse white for your flat.
Yep.
Or the people that get really serious and go buy an artificial star.
Or you get a I use an LED light panel.
Yeah.
They work fairly well.
Well, you get the high temperature Cree lights, and they are really, really bright white. You have to make sure you don't get them with too much blue in them, though. But there's a funny relationship that the lights have gotten bluer, but the CMOS imaging chips have gotten less sensitive to blue and more sensitive to red. So they're not going to be as affected by the blue coming in from the white light.
Mm-hmm.
Funny how that stuff works out. Okay, so in the next couple of weeks, we've got some other presentations. Let me just rattle them off here. So next week, the topic is going to be a look ahead. I took this from an old original Star Trek episode where the pilot from the 1960s tells Captain Kirk, "Thanks for the look ahead," when he was showing him what could be in the future. And this is in order for people to better understand astrodynamics, in other words, the movement of all the things in the universe. We're going to describe, if I'm on Earth here at a particular time, and I wanted to look in the sky, where the Earth would be the next time somebody on Earth could look back. I know it's impractical as time, but just to understand the orbital and rotational dynamics of the Earth in our solar system and in the galaxy. What are all the angles that are involved? What are all the motions that are involved? And the best way to do that is to say, if I'm on a globe here, and I know I'm going to be hopefully on a globe in the future, what's the earliest I could look back at myself, and how would I, not mathematically calculate it, but how would I evaluate it to take into account all the different motions involved? So that'll be a look ahead next week. And then the following week, I've got people already in my medical device community asking about, can I get a copy of that? If you've recently been seeing what's going on with the NASA Deep Space Network, it's oversubscribed. The number of longer than expected duration missions and the fact that they're all over the sky, the available telescope time on the giant parabolic dishes at the 3 stations of the Deep Space Network is running out of time slots. If you remember when the Artemis 1 uncrewed orbiter went out to the moon, circled the moon a couple of times, and then came back, it took with it, I think it was 10 nanosats, little tiny satellites that sort of shotgun blasted out and did a lot of observing on different wavelengths and such of the moon. They were far enough apart that pretty much consumed the Deep Space Network for the duration of observing those nanosats. Well, there's 10 of them, and they're just far enough apart. That means you've got to have all the antennas at each one of the 3 stations, all pointed not exactly in the same space, but in the general same part of the sky. Well, what does that mean for all the other 40 plus missions that the Deep Space Network is already subscribed to? So we know that from the presentation when it was launched, the James Webb Space Telescope communicates with Earth about every 4 hours because it can't hold much more data than that. And it's flash storage. So it goes off and it shoots something. and then gathers all that over a 4-hour period. And then now it's pointing back at Earth, and the Deep Space Network is pointing up at it, and it can communicate back and send that data down. And it's not gigabit speeds, it's only megabit speed. So it takes some time to shoot all that back down to Earth. So that means that at least one of the antennas has to be pointing out at L2, wherever L2 is at that time, in order to communicate scientific data from the James Webb Space Telescope. Well, what did it do during the Artemis mission? It lost that data. Well, if it can only hold 4 hours worth, and every 4 hours it takes a dump of the 4 hours worth, if you can't point an antenna at JWST for a good 3 days, what do you do with all the data? You got to throw it on the floor. So there was an audit in May of this year of the availability of the Deep Space Network. And what they found out was it's seriously oversubscribed, and they're already essentially throwing data away. The antenna is pointed somewhere else, and the data is coming in from somewhere else and just not receiving it. So what we'll do is have a presentation on a commercial alternative to the Deep Space Network. When the Deep Space Network was first fully fleshed out, it was the 1960s. And the only way we would do astronomy is big bada boomba dishes. And each one of the 3 sites has like the very big dish and then 3 smaller dishes. Well, you don't have to do that anymore. You remember us talking last week about LOFAR and about the flat panel array over the large area? Well, what if you had a bunch of those spread around the globe, and you could electronically steer wherever you wanted, and you were gathering all the data across all the bands that you could? Well, if that was the case, you could create virtual channels. So you could actually have the arrays picking up signals over a very wide spread of space from every communicating device that's up there in that view, gather all that down, and then using supercomputers at the site, separate out all the individual feeds for each one of the mission operations offices simultaneously. You cannot do that with the Deep Space Network as it's currently designed, because their approach is, I got one satellite, I point an antenna at it. How long do you keep it there? As long as I need to talk to it. Well, that's a waste of a huge resource that you dedicate to just one thing. We have newer technologies. We have, synthetic aperture radio communications. We have virtual channels. We have cryogenically cooled wideband receivers. We have all this technology at our disposal. We don't have to create new technology. We just have to package up what's there and deploy it. But of course, that'll cost billions of dollars and take a long period of time. So let's start now. So I give us an approach to how would you dip your toe in the water to get it cooking? I'm not going to mention the next 2 because they're so far off that I don't have a lot of detail on them. That is, all photons have unit energy, and then me re-reviewing the telescope smart camera because there's a lot of YouTube videos out there right now of ZWO and their new line of low-end. It looks like just a chunk of metal with a lens on it sitting on a tripod. There's no real telescope, so to speak. It's just there's so many advancements in cameras and in optics that you can now build it all into a device that just looks like a brick of metal, and it has one part that turns one way and the other part that turns the other way. That's your whole telescope, including the camera. So once the reviews start coming in for that stuff, I'll take a look at that. Okay. Any other topics? Any comments before we close?
Thank you.
Thank you very much. That was so heavy, I had to hurt you.
Hearing nothing else, thanks everyone and good night.
Good night.
Good night.